And only with discrete equals.
Okay. You can't do this either, I'm not tall enough, Dave.
I didn't do that one.
I think that was,
Yeah, look, all right.
for closest.
Yeah.
So today we'll do electrodynamics. In one day, I think. All the electrodynamics in there. But for us, it's just a way of taking Maxwell's equations and writing it in a covariant form. So, okay. If you recall, the divergence of the electric field is rho over epsilon naught. There are no magnetic monopoles as of now, today, just yet. Del cross E is Faraday's law. And so, del cross B must also have a dE dt. But curiously, I need to put some constants. And the constants are 1 over c squared and mu naught. Mu naught and epsilon naught. So c squared is equal to 1 over mu naught and epsilon naught. Okay? So if you haven't had E and M, this is what you need to know. E and B are vectors. J is a vector. Rho is a scalar in this formalism, and epsilon naught, mu naught is a constant. I think I know the answer, and it should be you're familiar, but just for clarity, do you know what divergence and curl is? Okay, good. So obviously this doesn't look like what we have seen. And I should also tell you the Lorentz force is Q times E on a charge plus V cross B. It is V cross B, and I just wrote it out of habit because, you know, when I teach E and M, I teach out of Griffiths. But for us, we have used. Okay. So now the question is, how do we put this in a relativistic fashion? Fine. There are two parts of the story. One part is what we will do. The other part is, fine, you can make it look relativistically correct. But is that how it works? So there are experimentations behind it. Furthermore, in the last chapter of Griffith, so if you've had E and M, I didn't get to the very last chapter. In fact, I think I'm missing 2 chapters. I think, maybe even 3, I don't know. 10, 11, and 12. Hopefully next time I teach, I get to 10 or something like that. What am I trying to say? Yeah, so Griffiths actually, that's a great book on special relativity. It's 1 chapter, if you've had E and M. So he actually motivates theoretically why electromagnetic fields should transform like they do, even without experimentation. And when you read his explanation, it is very clear, and you should be compelled in the argument. But if you're not, understand this, end of the day, this is physics, it has to be verified. And it has to be verified. Okay, so we have 4-dimensional space-time. Yeah? We have 3 E's and 3 B's. What do you do with it? You have to put it, you cannot make a 4-vector out of it. If you write it as the next thing beyond a vector is something like eta, a matrix. If you have a matrix, how can you ensure that you only have 6 things? Because we don't want to separate E and B anyway, we know this. mean, we see this here. A time-dependent B generates an E, time-dependent E generates a B. So one person's E, by moving, could be another person's B. So they're not separate. So the next step beyond a 4 vector is perhaps a matrix, sort of a tensor with 2 indices. But we need to make sure it has only 6 components. Fine. So that's exactly what we do. I will define the Maxwell field tensor. And we'll verify that it will reduce to Maxwell's equations, mind you. So it is defined to be F mu nu. And what we will do, so I'll put the parentheses at the end depending on how big the board is. So I'll take the diagonal entries, and you'll go, well, how can you do that? Because if you do diagonal entries and then you do a Lorentz transform, can you get diagonal entries to be 0? We'll show that it ends up being 0, because I'm going to pick all diagonal entries to be 0. If I remove diagonal entries, again, I should only have 6. So what I do is the following. Again, all of this has to be verified. Now I'm just defining it. And then, I'll tell you how this is not difficult, but that's why I needed to put this over here. Okay, so well, then we require this matrix to be anti-symmetric. What do I mean by that? When I do that, let's see what happens. Now I think this becomes minus EZ, as a matter of fact, this becomes minus EX minus EY. And so this becomes what? BY. No, am I putting this in the right place? No, this is minus BX.
Minus BX should be in
I should put it lower. This will be minus BX, and this will be minus BZ.
Also B1.
And BZ. This will be B1. Is that correct?
Is the one at the bottom left Y or?
That's supposed to be
Easy.
Z, sorry. The way I did, this is the problem. I didn't write nice little rows. So this is minus BX. We verify that this is in fact the case. Minus BZ, BY, minus BX. This is the case. So look at this. For example, F00 should be equal to minus F00 if I swap 0 and 0, right? So which is the only number that's equal to negative of that number? 0. That's why this is 0. As a matter of fact, F11 is minus F11, so the diagonal entries. Okay? And now you can see F01 is minus F10, because that's exactly what we did. Of course, we need to show, when I say we, I mean you, need to show that we're going to define a transformation property. If we define F to be an anti-symmetric, you guessed it, anti-symmetric tensor, then you want to make sure that when you transform F mu nu into another coordinate system, another frame, it has to continue to be anti-symmetric. So when I go to my office right now, I'll add to that problem in the list. Okay? Now, all right, that takes care of it. We haven't done anything, I just called it this, right? No meaning to be attached. And go with it a moment. Now we have all the fields taken care of. There are a few missing things. Correct? The question is, what do I do with that? verify that all the epsilons and mu's are correct. I may provide some correction here. Tomorrow, I might put an epsilon, or it seems like those epsilons and mu's are missing. This may be in another coordinate system. Okay? So, I mean, of course, if you pick a coordinate system where mu naught and epsilon naught is 1, we're good. But that's not how I wrote it here. So maybe what I'll do is go to a coordinate system where mu naught and epsilon naught is 1. But that's dangerous. If I do, C is 1. But I'm putting C explicitly. So please look for a correction on this one tomorrow meeting, the next time we meet. And then for J, I'm going to do a 4 vector. And that's easy, somewhat. These are triads. I have 3 components here and 1 component here. And knowing the intuition of, for example, U mu is C gamma gamma U. With this in mind, I'm going to put C rho and J. I've just defined it. You know, I can define anything I want, right? Yeah. Okay, and then we're going to do the postulate. Suppose, well, we know that this is what happens under Lorentz transformation. And if F is to be a tensor, then F bar mu nu X bar, X bar, the new coordinate. Can you help me? Assume that it's a tensor. I have to show that it satisfies Maxwell's equations, of course. But if I did assume this, what would the right-hand side be? Help me write the tensor transformation law. If you take F mu nu and wrote it in another coordinate system, what would it be? I mean, write the equivalent version of this. Use tensor transformation laws and tell me what it will be. I'll do one step. Let me clarify what it is that I'm trying to ask.
Okay. So
Now help me fill in.
lambda, you'll have mu sigma, we'll say.
Mu,
Mu.
okay?
Mu sigma.
Sigma where?
Down low.
Down.
And then you'll have nu gamma, we'll say.
Let me just do, how about this?
Alpha and beta, yeah, okay. And then it'll be f of alpha beta up.
Yeah. Good. One
Of
thing
x,
missing?
Of x.
Very good. Presumably, if Maxwell's equations satisfy a tensor law, well, that's what it should. That's not so much our worry now. As I mentioned before, Griffiths motivates it and experiments verify it. So the transformation law is not worried. I'm more worried about how does this describe Maxwell's equations. Well, what do you think this is going to be? This should be easy, right? It's a vector.
Lambda, mu.
Yeah, mu is good. Yeah? Good. So whatever it is, again, my apologies, there might, I don't know if there's a mu naught or divided by mu naught or epsilon naught here. I'll fill this matrix out the next time we have class. As a matter of fact, Monday there's no class, right? It's exam.
I thought you were going to say no class, no meeting.
Well, I mean, we can take the exam into
no. I meant what I said, we have an exam. No class, but exam. Okay, now, what our goal would be is to write out Maxwell's equations in a relativistic fashion. Well, oddly enough, did I write out, curious, let me see how that works out. All right, I'm going to define this object. Today is day one of seeing it. If you stay with relativity, you will see this and you'll understand it geometrically what it means. It's an incredible object. It doesn't look like it. Today it just looks like why. Well, that's how we often begin. I'm going to define. Oh, first of all, let me use mu lambda. What I've done is what? Lowered the index. How did I lower index?
Using the eta.
Using eta. Yes. Thank you. Tell me what.
Be equal to eta.
Oh, someone else. So last time we stopped with Veronica's. Okay.
So just do the trend lambda.
No.
Or is it not?
I'm lowering index. Gracie,
We use an eta to lower index, right?
is that a question or an answer? I
It's
was
an answer.
good. So tell me what goes.
Hold on, give me this. Well, I'm losing, you can always pick someone else.
No. I want to pick you. I'll tell you why. Because you surprise me all the time. You do things correctly. You'll sit as if you're not paying attention, but then
Following you, right?
then you'll just give an answer. And I'm often
It's
pleasantly
usually up to me,
surprised.
though.
What's that?
It's usually up to me, this is not usually you calling on me for an answer.
No, when I do, you respond. All right, I might have to move on to David's stuffed animal. Who might give me a correct answer. Noah.
I'm still looking.
Okay, I'm going to change this around. Anyone. No, anyone, not Jackson. Zachary, please.
Is it eta mu down?
Mu.
Mu?
Okay, I'm going to just write down what you say. We're going to erase a little bit, but that's okay.
Shoot, I was gonna say eta alpha beta down.
That's,
Wait. is
I
it-
like the indices generally written.
Yeah. Like it. So is alphas like are they supposed to be mixed? Like
Well, why don't you, yeah, try that out.
yeah. Okay. So the first one is mu down alpha up.
Alpha up.
Or wait.
You don't know.
No.
No summation there. Alpha doesn't cancel out.
Yeah, how do you get summation? Up and down.
Oh.
Yeah. All right, chapter 3 exam comes after chapter 2 exam, huh? Okay. So by this I mean, couple of things. What does this mean? It's short for this. Yeah? Because we'll have just, now derivatives are just starting, yeah.
Are the brackets just visual? Like that's just to show that you're
No,
going
no,
down?
no, no, let me explain what
Okay,
this is.
there is an arrow. Okay.
Yeah. So it's a 1/1. There are 3 of these. Like I said, this has a big life of its own. Huh? It's called exterior derivative. But it is d mu f nu lambda. And then every combination with the order of the permutation. What does that mean? Minus. I'll tell you why minus. I'm replacing nu lambda with lambda nu. Yeah? And then I'm going to go from mu to nu. So then I put plus d nu. I have, my nu was taken care of. I have to go cyclic, lambda mu. And then the other combination with the minus sign. Mu, lambda. Tell me, if I follow that pattern, what will be the next 2 terms? I'll open it to anyone on the floor.
Oh, can we just say that?
Huh?
Can we just say that? So d lambda,
Lambda.
Lambda.
Oh, sorry.
f mu nu,
F mu nu.
minus d lambda f nu mu.
D lambda F mu. That's exactly right. So if you notice, there are 6 terms, and that explains why we divide by 6. Exactly. Yeah, 3, and we get the 3 from here. Once we learn about derivatives in general relativity using tensor calculus, you'll see that coordinate derivatives don't mean anything, have no physical meaning. We begin by using something called covariant derivatives. But then you will learn, because they don't depend on coordinates, but then you will learn that this kind of anti-symmetric, it's very anti-symmetric, right? Combination is coordinate independent, regular partial derivative. And we'll see what all of that means. But I can simplify this already. Notice I've taken the factorial off. I'm going to write the first 2 terms as, why is that? Remember, I've taken, let me do it this way, so that you see it. I'll erase it at the end. The first 2 terms, why is that?
Because they're anti-symmetric. It's
Yeah, f nu lambda
No
is
what?
minus f, okay? So now, you can see now I'm going to erase this. I'm going to take the 2 away and make this a 3. All I need is the positive terms. d nu f lambda mu plus d lambda f. That is this object. I don't want you to think of nu. I don't want you to think of this being equal to that. Okay? But this is what you should have in mind. The complete, all permutations. Okay? If you ever get to a field called exterior calculus, this would be the exterior derivative. It's a very, very powerful object. This is in fact the curve. Okay. I call it a theorem, and again, there's no need to call all these things. Theorem is just a calculation. The homogeneous Maxwell's equations. Do I spell homogeneous correctly? I don't know. But it's a little bit of a scribble, it could mean anything. Are given by guessed it, What are the homogeneous Maxwell's equations? So I just erased it. Divergent, whatever is equal to 0. So they are in fact, divergence of B is equal to 0, and yeah, equal to 0, and curl of E plus dB dt. So these are the ones without rho and j. These two equations are given by that.
So do the brackets just mean it's cyclic? So it's saying like,
Cyclic, but anti-symmetric.
okay.
Cyclic would mean, mu nu lambda, nu lambda mu. It does work out in this case. But you, like I said, you should think of this as an anti-symmetric object. Things are very nice with anti-symmetric objects. In fact, that this generalizes curl in any dimension. As a matter of fact, it has to, because you see there's curl over here. Yeah? Okay. You know how curl has a formula in Cartesian coordinates? It's easy to write down the matrix and write down the curl. If I ask you to do the same in spherical coordinates, would you know exactly what it is? No. So, but if you know geometry, and we'll slowly learn it, everything works in any coordinate system. Okay. All right, proof. So first I'm going to do is pick a trivial answer. Pick mu equal to 0 and lambda equals 1. So I would get 1/3. D0 means with respect to CT, huh? D0 F01, correct? Plus D nu 0 F10 plus D1 is really dx, correct? Partial with respect to x, and f0, 0. So some of these have trivial things. f00 is 0. f01 is a negative of f10. So this, for example, this combination yields no result. Okay, then I'm going to pick a choice of mu equal to 0, mu equals 1, and lambda equals 2. All right, I'm just going to write it down. Help me out here. 1/3. It's going to be equal to 0, so I don't care about that. D0 F12 plus dx F20 plus dy F mu nu 0, 1. So I erased this, but you have it in your notes. What is F12?
F12 is.
Let me look at the.
Positive BZ? No. Yeah, positive BZ.
I'm hoping you're right. What is F20? Minus EY? Y F 0, 1
X.
X. This is nothing more than the Z component of I'm beginning to think that there's a 1 over c here. I have to clarify that. Yep, there's a 1 over c. So my units were not very carefully picked. I will update the notes to have the correct notation and put it on the web page. Is that true? What is a z component of, so x hat, y hat, z hat, del cross E, so partial x, partial y, partial z, ex, ey, ez. What's the z component of the curve?
It'll be
It is dx ey minus dy
which is the opposite.
which is the opposite, but that's fine, because, so d, right. And so what is F12? Is it plus BZ or minus BZ?
I think
There's plus
the
B.
last one, F01 is minus dx.
I'm sorry? Yeah,
0, 1,
Yeah.
that would be the first row,
that is EX.
second column.
And then the
Positive.
And then 1, 2 would be positive BZ, 2, 0 would be negative BY.
Yeah. And
Those are all right.
Yeah.
Those are the right indices.
Are we missing a minus sign? F12. Let me check my F12. 0, 1. It is plus BZ. Am I missing something? No, it is correct, right?
I mean, it's the reverse of that, though. Or the inverse.
No, why is that?
It's negative when it should be positive.
Oh, right. Well, let me see. Z dx ey minus dy ex, that's right. Well, guess what? I may have to fix the entire matrix. F mu. Oh, right.
Do we have it reversed?
No. This is F down. You will show. I wrote this down, but I never wrote the matrix. Remember F mu nu, eta mu alpha, eta nu beta, F alpha beta.
Okay.
And that is equal to 0 minus EX. I need to fix this constants everywhere. EZ. This is clearly only correct modulo some constants that I'll fix. And because of that, this is what I'll do. Minus BY minus BZ 0 BX and then BY minus now let's put this in correctly. Remember we lowered the index.
Yeah.
What is F12?
Still BZ, still positive BZ.
0, 1, 2.
That's 3.
Oh, 1, 2. BZ, fine. So this is BZ. F20. EY.
Positive by this time.
That takes care of it, right?
And then the next one should be negative EX, yeah. is just a Z component.
Yeah, it is a Z component. Yeah, so my apologies. You know, as a matter of fact, the next result really won't affect what I'm doing, but I hate the fact that there was no clarity there. I didn't put the units in correctly. So we're 10 minutes shy. I want to stop it right here. And so I fixed my notation clearly. So even here, this may not be correct when I lower. But the signs are correct. For example, we have a little bit of time, so let's see how this came about, for example. So this would be F01. So that would be 0 alpha, 1 beta, F alpha beta. This means alpha can only be 0. This means eta can only be 1. Okay? But this is negative and this is positive. So that's negative F01. So if the other one had EX, this is going to be EY. Will the spatial component be affected at all? Let's do this. What will only the electric field? That's right. Only the electric field gets a reverse sign. What happens to the magnetic field? See, magnetic fields live in this spatial part. Correct? So let's do, for example, F23. Well, it's eta 2 alpha, eta 3 beta, F alpha beta. This can only happen when alpha is 2 and beta is 3.
So eta literally acts like a
So when you bring this down, whenever you bring vectors down, what happens? The time component becomes negative. Here what happens is not just a time component, but the row and column that has time components become negative of each other. So the E's simply switch. B remains the same.
Does B not have time components?
I'm sorry?
Is B not time?
No. Look at any of this. This is, for example, 1, 3, 1, 2.
Yeah.
So there's no 0.
But like thinking, just like conceptual, does
What?
B not have any time dependence? Like would it not?
Not time dependence. This is the time column and time row, meaning this is F 0, 0, in this case F 0, 0, F 0, 1, no, F 1, 0, F 2, 0, F 3, 0. Meanwhile, this is F 0, 1, F 0, 2, F 0, 3. So there's 0 only in these guys. And eta has a negative component only when there is a 0 in it.
Yeah.
So eta, as a matrix, it's diagonal. Correct? So when you lower F, you get the electric fields switch signs. The magnetic fields does not switch aside. This does not mean, I think you said, is magnetic field not time dependent? It's nothing to do with time dependence here.
Okay.
Because that comes about here.
Yeah. It's just the electric field is the only one that's affected by this fact that it's in the time, because it's in the time column and row.
Yeah.
Okay.
So I think what I've done is correct, provided I set units where mu and epsilon naught is absorbed. But I need to restore that. I think it might be easier to restore it that way. Let me see how I to it, I want to provide more clarity. So for that, we'll just end a little early today. But any questions?
So is 8 just a Kronecker delta for indices?
I'm sorry?
Is 8 just a Kronecker delta for indices, basically?
Almost Kronecker delta.
Yeah.
Yeah.
It's, I mean, it doesn't have, infinite range. It only has,
Yeah,
0 to 4,
it
or
is.
0 to 3.
It is almost like Kronecker delta. It's very special. It is invariant under Lorentz transformation, right? But it also is a Lorentz transformation.
Yeah.
It's not orthochronous. It flips the time component. So the very Lorentz transformation that is a time reversal is our invariant object, while we're trying to get away from time reversal completely. So, good.